Today we're going to take a look at function basics, including the average rate of change of a function and the difference quotient for a function. Much of what we do today is going to be a complete review of topics that you already know from Algebra 2. First of all, what is a function? Well, a function is a relation that relates, let's say, x and y. A function is a relation such that for every x in the domain of f, there is one and only one value of y. Graphically, a function passes, what we say passes, the vertical line test. And that means that any vertical line that we draw through the curve, through the graph, passes through exactly 1 point, no more than 1 point. So for a few examples here, every vertical line that we draw through this graph passes through exactly 1 point. Every one. I cannot draw a vertical line through this graph that passes through more than 1 point or fewer than 1 point. Okay? Same with this one. Every vertical line, no matter where I draw it, passes through exactly 1 point, right? For this curve, though, every vertical, well, not every, but the point is I can draw a vertical line that passes through more than 1 point. So this one is not a function. It is a relation. I can completely draw a curve. I can do lots of things with it. It's very useful, but it's not a function. Both of these are functions. Okay? So graphically, determining if something is a function or not is very easy to do. All right, algebraically. To determine algebraically if we're given an equation, not the graph, and if it's something that we don't immediately know the graph of. If it's something that we don't immediately know the graph of, then algebraically how to determine if something is a function, if a relation is a function, is go ahead and try to solve for y, or imagine solving it for y. When you solve it for y, do you get one and only one equation? That's the key. So for this one, I actually know already what this graph is. This is the graph of a parabola pointing up, right? Actually, it's a parabola pointing down. But because when we solve for y here, if I solve this for y, now move the 4 over, move the x squared over, divide both sides by 3. I get one and only one equation for y. So yes, this is a function. Okay? This one. When I try to solve this one for y, and I can solve it for y, sometimes we cannot solve it for y, but I can solve this one for y. I'm going to subtract the x cubed over. Multiply both sides by x. Divide both sides by 3. And now, how do I get the y by itself? I need to take the 4th root of both sides, and therein lies the problem. When I take the 4th root of both sides, I will need plus or minus the 4th root of that other side. And that destroyed the possibility that this was that this relation is a function. So this is not a function. Okay. When you have a y, when your highest power of y is an even power, it's going to destroy the functionality of that relation. Okay, so That is what makes a function. Evaluating a function. So here I'm given a function, and I'm asked to find several different values of this function. So let's go ahead and remind ourselves how to do that. F of -4, I am replacing the x with -4. So I go here and I replace every x with -4. And then we can simplify. -8 plus 3, so this would be 12/5. So when x is -4, f, or the y value, is 12/5. Let's find f of 1/8. Okay, if I put 1/8 in for x, this is going to be 3/8 in the numerator. This is going to be 2/8 plus 3, and I know that reduces to 1/4, but since I have an eighth up here, I'm going to leave this as 2/8 because of what I'm about to do. To simplify this, I'm going to multiply top and bottom by 8, and when I multiply top and bottom by 8, I get 3 over, okay, distributing here, these 8's cancel out, I'm left with a 2 plus 24, so this is 3 over 26. Okay, f of x plus h. So we are replacing x with x plus h. So I go over here and I'm replacing both of these x's with x plus h. So that will be 3 times x plus h divided by 2 times x plus h plus 3. And I could distribute. Okay, I could do some things with this, but since it's not a multiple choice question where I need to get to anywhere, I think I'm just going to leave it like that. I don't think that distributing is going to help, quote, simplify very much here, so I'm just going to leave it like that. Let's come now and try to find f of -3/2. When I put -3/2 in place of x, I'm going to have 3 times a -3/2 is -9/2 on top. On the bottom, I have 2 times -3/2 plus 3. And 2 times -3/2 is -3 plus 3. That gave me a 0 on the bottom, didn't it? That means that this value, this function value, does not exist. This is undefined here. It does not exist. Which means that -3/2 is not in the domain of this function. Whenever we get a value that does not exist, it's not a real number, then we say that that value is not in the domain. And that leads us to our next topic when we're talking about functions, and that is domain and range. Okay, so in the last example, this did not exist. That means that -3/2 is not in the domain of f. The domain of a function is the set of all values of x which make f a real number. The domain can be described explicitly, or it can be implied by the expression used to define the function. For example, if I just give you this function, I am implying that the domain is all values of x 0 to infinity, okay, greater than or equal to 0, because that's what would make this function real. So it's implied. All right, so unless you're told otherwise, we have this implied domain. Okay, all right, we can write the domain and the range using interval notation, inequality notation, or other kinds of notations, as in verbally. Like I said right here, verbally, the domain is the set of all real numbers greater than or equal to 0. That is a completely fine way to state the domain. Or We could have done it with interval notation, or we could have done it in inequality notation, which would have been x is greater than or equal to 0. That's inequality notation. Know all of those because of multiple choice questions. You want to be able to get that answer. All right, graphically, to find the domain and the range of a function, to find the domain, we observe what values of x are being used to form the graph. The range are the values of y which form the graph. So here, the domain, all the x values that are being used they begin with -3. Now, the last one on this graph is 13 point something. Does that mean that it ends there? No. This is implied to continue. You're not going to see arrows, but they are implied. All right? So the domain here would be, we can do it in interval notation, -3 to infinity. We could do it in inequality notation, x is greater than or equal to -3. Or we could say it verbally. X is the set of all numbers that is greater than or equal to -3. The range are all of the y values that are being used. And y, the very lowest y possible is 1. And again, even though it looks like it's only going to 5, we know that this is going to continue forever. So the range will be from 1 to infinity. Interval notation, inequality notation, verbally, all work. Know them all. Analytically, to find the domain. Okay? Analytically, if you're asked, and you would only do this if you're asked to find the domain because of that implied domain. Okay? When you're finding the domain of a function, the first thing I do is I look to see if it has a denominator, because any value of x that makes the denominator 0 must be excluded from the domain. The next thing I look for are even-powered roots. If you have an even-powered root, then the interior of that root must be positive, or 0, greater than or equal to 0, the interior of that root. Let's do this one first, though. What is the domain? The numerator does not affect the domain. The denominator does here. So this looks like it can be factored, and it can be factored. However, I don't care. I'm not going to waste time factoring something that I don't need to. Down here, though, I need to find out what values of x make the denominator 0, and I need to exclude those from the domain. So I am taking the denominator, setting it equal to 0, and solving for x. So add 9, divide by 4, take the square root, and I find that x is equal to, so when x is positive or negative 3/2, our denominator is 0, therefore positive and negative 3/2 they are not in the domain. So the domain, I could write this several different ways. For me, the easiest way to write this is all values of x such that x is not equal to positive or negative 3/2. That is a perfectly fine way to state the domain. Okay, another way to write it is with inequalities. So, or interval notation. And to do this interval notation, let's think of a number line. Here's negative 3/2, here's positive 3/2, and I don't want those, but I want everything else. Okay, so I want from negative infinity to negative 3/2, not including the negative 3/2, we always use parentheses around infinity, union with negative 3/2 to positive 3/2, union with 3/2 to infinity. And that's fine. That's interval notation for that domain. We could also use inequality notation. Okay? What is the domain of this function? Well, the first thing I'm going to do is exactly what I did over here. I'm going to see what values of x make that denominator 0, because I know I must exclude those. X squared minus 4 is 0. That would make x plus or minus 2. So I know that the denominator cannot be 0. So x cannot be plus or minus 2. Okay? Now for this even-powered root. For the even-powered root, I have 8 minus 5x that must be greater than or equal to 0. Which means that if I subtract the 8 over, divide by negative 5, when we divide by negative, we change the directions of our inequality sign. So we have x is less than 8/5. So that's part of the domain, but I also need to consider this. Let's think of a number line. So less than 8 over 5. 8/5 is almost 2, right? There's 8/5. And I want less than or equal to. Less than or equal to that, right? But I don't want 2 or negative 2. Well, 2 is beyond this, so it's not there anyway. But negative 2 is in here. So I don't want negative 2. Negative 2. Okay, so interval notation for this domain. Negative infinity to negative 2. Don't want negative 2. Union with negative 2 to 8/5. I don't want negative 2, but I do want 8/5. And that's it. So that's domain. Zeros of the functions of a function, also called roots of the function, are values of x that make y 0. So to find zeros of a function, we take our function and we set it equal to 0 and find x. To make this vaguely interesting, I have chosen some problems that force us to factor a little bit. So here, when we're factoring this, we need to do it by grouping because we have 4 terms, yeah? I'm going to take the first 2 terms and factor out what's in common. So what's in common is a 3x squared. So I'm taking out 3x squared from those first 2 terms. I'm left with an x from the first term and a minus 2 from the second term. From the next 2 terms, there's a 2 in common. I'm going to factor out a negative 2 because I want what's left to be an x minus 2. So I'm going to factor out a negative 2, and what's left will be an x minus 2. Make sure that when you distribute back, you get exactly what you started with. And this is equal to 0. Make sure you keep writing equals 0 here. Don't lose that equals 0. Otherwise, what you're doing doesn't work. Okay? All right. Now, I have 2 terms. I started with 4 terms, and now I have 2 terms. What's in common with these 2 terms? What's in common with these 2 terms now? Well, the x minus 2 is in common. From the first term, when I take out the x minus 2, I'm left with 3x squared. From the second term, when I take out the x minus 2, I'm left with minus 2. Still equal to 0. So now we have two values, 2 expressions that are multiplied together to equal 0, which means that either x minus 2 is 0 or 3x squared minus 2 is 0. So x is 2 or x squared is 2/3, which means that x is plus or minus 2/3, and these are the zeros of the function. Oops, square root of 2/3. Square root of 2/3. Let me comment on that. Square root of 2/3 in a multiple choice question. That may be how they write the answer. Or they might rationalize that denominator. So really quickly here, if we have square root of 2 over square root of 3, which is the square root of 2/3, if I multiply top and bottom by square root of 3, it rationalizes, it makes the bottom rationalize. It rationalizes the denominator, because square root of 3 times square root of 3 is 3. Up on top we'll have square root of 6. So they might write this as positive or negative square root of 6 over 3, rather than positive or negative square root of 2/3. Okay, next up. Average rate of change of a function. So now these last two topics are getting into really pre-calculus concepts. This might not be something that you focused on in Algebra 2, but we're going to be focusing on it more now because we're getting you ready for calculus. So average rate of change of a function. The average rate of change of f on an interval, you have to be given the interval, is just your change in f over your change in x. So that would be f of b minus f of a over b minus a. This should look very familiar to you. This is your formula for slope. Average rate of change is the slope of the function between 2 points. Slope of a function, that is slope between 2 points. Okay? So, to find the average rate of change of this function, p of x, on the interval from 1/2 to 4, when I see average rate of change, I think change in p over change in x, which is going to be p of 4 minus p of 1/2 divided by change in x, 4 minus 1/2. So let's come find p of 4 and p of 1/2. Well, p of 4 is, if I put 4 in for x, that's 8 plus 8. I have the square root of 16, which is 4. So p of 4 here is 4. What about p of 1/2? If I put 1/2 in for x, 2 times 1/2 is 1. 1 plus 8 is 9, and then square root of 9 is 3. So p of 1/2 is 3. And then on the bottom I have 4 minus 1/2, which is 3 1/2. I think I might just leave it 4 minus 1/2 for my purposes. And then for a multiple choice question, I would multiply top and bottom by 2, and that is 2 over 8 minus 1, right? Multiplying that out, so that is 2 over 7. Average rate of change. Our last topic is the difference quotient. Difference quotient. The difference quotient is another calculus topic. The difference quotient of a function is found by determining this expression. That is the difference quotient. In calculus, we use the difference quotient in the definition of the derivative of a function. We let h get infinitesimally small. So if h is infinitesimally small, that means it's very, very close to 0, but not 0. It can't be 0 because we cannot have 0 on the bottom. But if if h is infinitesimally small, then this becomes f of something very close to x minus f of x, so the numerator is getting very, very small, and the denominator is getting very, very small. That is actually the definition of the derivative of a function. Okay, the directions here say to find the difference quotient for g of x. They give us the formula for g of the function equation for g of x. All right, so I need you to memorize this. And to me, it's very easy to memorize. It looks like f of x minus f of x, except we have this plus h and an h. So f of x minus f of x, but this is an x plus h all over h. Okay? So for g, we'll have g of x minus g of x, but here we'll have an x plus h. And then we have h on the bottom. Okay? So, g of x plus h. Well, g of x plus h, I'm replacing x with x plus h. So I replace both of these x's with x plus h. 3 times x plus h squared plus 4 times x plus h minus 7. That is just the g of x plus h. Minus, and now we need g of x. Well, g of x is right here. Since we have this minus, be careful because you're subtracting this whole function, so we're going to have to change the signs. But so that I can actually see g of x here, since I have to do some work anyway, I'm going to write g of x in parentheses. And that is all divided by h. Okay, now, and again, let's simplify this. All right, these will be multiple choice questions, so we'll have to simplify, clean this up. So I'm going to square this binomial. When you square that binomial, you're going to get an x squared, and you're going to get an h squared, but you also have that middle term, right? That plus twice the product of those. Multiply these and double it. That's how when you're squaring a binomial. Plus h squared plus, distribute the 4 through these parentheses, minus this 7. And now I'm going to go ahead and distribute the minus through the next set of parentheses, all over h. Okay, well already here I noticed that there's a minus 7 and a plus 7, so those cancel each other out. There's also a plus 4x and a minus 4x, so those cancel each other out. Let's go ahead and distribute the 3 through these parentheses. 3x squared plus 6xh plus 3h squared plus 4h down here minus 3x squared all over h. And now I see that I have a positive 3x squared and a negative 3x squared. So those are gone, and everything else has an h in it. When you're finding a difference quotient, that's going to always happen. You're going to get terms with h's that you can factor out an h on and reduce with this h on the bottom. So that's what we're going to do. I'm going to take an h, that's what's in common up here. I'm taking an h out of everything on top. I'm left with 6x plus 3h plus 4 divided by h. And now these h's cancel, and I'm left with 6x plus 3h plus 4. So I have a question for you. What happens now if h is infinitesimally small? If h is extraordinarily close, extraordinarily small, so close to 0 that it's almost 0, then this becomes just 6x plus 4, and that is the derivative of that function. So a little sneak peek into calculus on day 1 of precalculus. That's difference quotient. That ends our quickie review of functions.